Okay, so hello everyone. So thank you for attending this seminar talk. So it is really my pleasure to introduce today to Alejandro Cadrenas Avendano, who is from Colombia, and currently he's postdoc researcher at the physics department at Princeton University, and also research associate at the mathematics department at the Fundación Universitaria Conrad Lorenz in Bogota, Colombia. So today he's going to talk about modeling of observational signature of compact objects, particularly the Kerr and black hole rings. So Alejandro.
Thank you, Camilo, and thanks for this kind invitation. Let me share my screen and move this Zoom thingies to the left. Okay, can you see my
yes, we can see it, sure. Mm-hmm.
Okay, perfect. Okay, let me start. So thank you for the invitation. Thank you, Camilo, for this invitation. And if you guys want to have your cameras open, that would be a little bit more helpful. And then please feel free to interrupt me at any point with any question. So I'm going to talk about a recent project I did with Henry Xu. He's a grad student here at Princeton University. And Alexandru Lupșească, he was here a postdoc, but now he's a professor at Vanderbilt. And the idea here is to study and revisit these ideas of photon rings that have had a lot of attention in the past year. So I'm going to comment on why we are interested in this type of observables and why do we care. And I'm going to basically try to address the question, theoretically at least, if we can use black hole images to test or understand fundamental physics. Okay, so let me start with my background. I did my PhD on tests of general relativity, and not because I don't like general relativity, just because I want to understand the properties of GR. And the idea is that, how can we do this? There are at least two venues. One is going to be a theory specific, meaning that I'm going to look for what are the particular properties or pillars of general relativity and try to modify them or break them or violate them. So there is a nice theorem by Lovelock in which you have certain assumptions, hypotheses, and then the only result is general relativity. So GR, as you know, is a four-dimensional theory. There are no extra fields. It has certain symmetries and respect the weak equivalent principle. And that the theorem says, given these assumptions, the theory is general relativity. So if I want to proceed in a theory-specific way to understand or to test general relativity, what I can do is break something. So I can add extra degrees of freedom and then ended up in a solution or in theories like F of R, quadratic gravity, such as dynamical Chern-Simons, and scalar Gauss-Bonnet. I can also, for instance, break one of those symmetries and then ended up in a different theory like Lorentz violating, massive gravity, etc. So this will be a theory-specific way to do this. There is another venue or possibility, which would be theory agnostic. In this case, you don't necessarily have a theory, but you might want to parameterize something. Then one of the most famous cases is the PPN or parameterized post-Newtonian, in which you are going to write something that is called a superpotential, which is all the possible terms that you might add to a potential or different type of potentials that would be different from what we expect from general relativity. And this is very suitable for tests in the solar system. You can also do this, not at the level of the potential, but you can do it at the level of an observable. And in this case, it's the parameterized post-Einsteinian, in which now you are going to parameterize the, for example, in this case, the waveform. So you have an amplitude and a phase, and now you are going to put parameters for this amplitude and this phase. And your goal in this case is to constrain those parameters that you are enhancing your waveform template. So the first one is at the level of the theory a little bit, and the second one is at the level of an observable. And more recently, also, there has been a lot of attention in these parameterized or bumping metrics, in which you start from a solution in GR, let's say Schwarzschild or Kerr, and now you're going to add to this metric a parameterization. And there are different flavors and ways to do this. But the idea is that you have parameters that when these parameters are zero, you recover the GR solution. So it could be Schwarzschild or Kerr. Perhaps the most recent incarnation of these ideas is the Retsola-Shirenko for the spherical case, or the Konoplia-Shirenko-Retsola or Konoplia-Retsola-Shirenko for the axially symmetric case. So as I said, is a metric is not a solution of any theory necessarily. Actually, for the most part, these solutions, these metrics are not solutions to Einstein's equations, meaning that it's not Ricci flat. You might even change the Petrov type of the metric, but then remember, you don't have a solution. And this is more or less the different approaches you can follow. So let me, for the purpose of this talk and just to set the context and motivation, let me just tell you there is a metric by Renzola-Shirenko. There is another one by Johansen in which you have a parameter. Let me call that parameter alpha 13. I don't want to get into the details of how this metric is, but what you might want to know is that alpha 13 is a parameter that appears in the GTT component of the metric mainly. So the effects are through this GTT component. And as I said, this is a parameterization at the level of the metric. You can compute observables. And then when this parameter is 0, you recover a GR solution. And in this case, it could be a Schwarzschild or Kerr solution. But when it's not 0, you are going to have a deviation from GR. So if you follow this theory agnostic approach with a metric, you can, for instance, try to compute an observable. And then for this case, we compute it using the PPE, the post-parameterized Einsteinian formulas. You go and compute in the waveform how these parameters enter. This is just the conservative part of the solution. You assume Einsteinian radiation, and then you use, in this case, we use the first results of the LIGO catalog to put some constraints on this parameter. So as you see, consistency with GR, and then it has a particular error bound based on the, in this case, this catalog have like 10 events, but here you use the 5 most loudest one. And this is for binary black holes. Some other people have also worked extensively on applying this type of parameterization for electromagnetic observations. And in this case, you are observing a low mass X-ray binary. The low remains to, it's because the black hole you're observing has low mass in comparison to the big star that is actually providing the material. And then you can apply this to real sources, and then it provides a constraint. And what I want to notice here, and I'll comment this in a second, is again, consistency with GR. And then the error bars are different. That's why I have colored them in a different color. You can also go to a very different system in principle, supermassive black holes, apply the same game. You parameterize your metric, you compute how photons are taken to the observer. What they are doing here is also called the spectroscopy of black holes. You just want to see how these lines are shifted in the electromagnetic spectrum, and then you want to constrain given data how that parameter behaves. So this is for supermassive black holes. And more recently, part of the Event Horizon Telescope collaboration, they did an analysis of also in this sense. Now you modify the conservative part of the theory through a parameterization, in this case, Johansen, and then you return a constraint. And as you have seen in this slide, I have a color code these different experiments. And then the first thing I want to notice again, and I want to emphasize this, is consistency with GR. GR is so far the best theory of gravity we have. Okay, that's good. Now, the second thing is that, as you can see, the error bars are very different in all these systems. And what I want to notice is that there's a consistency between a large range of scales here and systems. This is binary black holes, low mass X-ray binaries, supermassive black holes. The systematics, the way these analyses are done are very different. And that's why this is very interesting to look as also as a consistency check. Now, this M87 using the EHC results, as you can see, this bound error is at 1 sigma as opposed to these 3 sigma ones. So you might want to think, why is that? And then the reason is like the errors, as I said, the systematics in all of these observations are very different. But here in particular, when you do this analysis for gravitational waves, you need the dissipative part of the theory. And the systematics here actually come from your ability to solve the field equations to get this radiation reaction. So in some sense, you know the theory of gravity, and in this case, you can parameterize the conservative part of it. But then our systematic is just because the way we are solving this equation. When we go to these observables in the electromagnetic spectrum, you have systematics because you now have the astrophysics, which is more dependent. And now you have a lot of parameters that they start making this degeneracy. For these particular 2 observations in the X-ray spectroscopy, you assume that you know the astrophysics. You assume a geometry for the disk, and now the only thing that you are changing is how light propagates to the observer. And that's why it gives the best constraints. But then remember here, these error bars are underestimating the systematic errors. And that's not the case for this nice observation of the EHT. Here, they are taking into account systematics, statistical errors as well. Because now you have different accretions structure. Now you are changing the astrophysics as well as changing the GR theory for how the gravitational theory for how light is propagated. So to summarize this slide, there are different ways to test GR. You can do this in a theory agnostic way. So far we have consistency, and we have different ways to do this. And then the errors, systematics and statistical of all these experiments are very different. And that's why they should be seen as complementary. So for the rest of my talk, I'm going to focus on EHT-like observables and to ask the question if we can use this type of images to test fundamental physics. And this image is the product of the EHT collaboration. And as you can imagine, and maybe you know, and I mentioned briefly, it corresponds to two things. Space-time, you need to assume a theory of gravity, and you need to assume an astrophysics for the plasma that's around it. And we learned a lot from these images. For example, we see a flux depression consistently with the notion of a black hole. We also got the scale. We know the scale of this image is roughly 40 microarcseconds. It has a particular width, like this one. Also has an asymmetric brightness, potentially related to the M87. It has a jet, and then it's spinning. We also know its inclination of the system. It also, this scale also gave us an estimate for the mass. So we know that the mass should be between 4 and 7 million solar masses. And then we know more or less that the peak intensity should be close, not necessarily at the ISCO, but it's a near horizon. So we are proving a lot of that. So this is a great image. This is a seminar result. And then the question, of course, we can ask is how can we use this type of measurements to test general relativity? And if you recall from my previous slide, the error bounds that we can put, at least in a theory agnostic way, are really large. So the question is there a way to try to disentangle the properties of these images that belong to the black holes and then disentangle them from the astrophysics? And there has been recently a lot of works trying to address this question. So let me focus on one very simple scenario to give you like a taste of the difficulties that these type of observations have. And this is a work in collaboration with that we did a couple of years ago with Adam Bauer, Charles Gami, and Nico Younes, where we study a very simple system. We have Bondi accretion. This is a spherical accretion into a black hole. And then the idea here is to, again, remember, I'm trying to see if there is a way to disentangle the theory of gravity and the astrophysics, and way if we can extract the parameters and disentangle them. So if you assume Bondi accretion, which is a spherical accretion, and then you assume your theory of gravity, then you can, remember, this is a very simple toy model in which now you're going to say, okay, my emissivity, and in this case, this is going to be my astrophysics, is going to be a power law of this way. So alpha is going to change how my black hole more or less is being illuminated. So that's going to be for this very simple system, spherical accretion. This is going to be my astrophysical model. So I can derive, and this is sort of similar, as of course, in a very simplified manner, what the EHT does. They need to calibrate. So you can derive a calibration parameter, which is going to depend on our characteristic. I'm going to tell you that in a second, divided by the impact parameter or the critical parameter. From the experts in the audience, this is also known as the boundary of the black hole shadow. So you can do this in a simulation. You can derive what is the R characteristic. In this sense, it's like the second moment of the image. You might want to more or less heuristically think about the width in this image. And you can also know, because you did the simulation in your computer, where this B critical is. So you can compute a calibration parameter. And this calibration parameter is the thing that's going to tell you if you observe something, you can always compute the second moment of an image. And from that, since you know the calibration parameter, because you did your analysis first, you might be able to infer where this impact parameter critical or the boundary of black hole is in the image. So you can invert this equation, and then this is going to be the goal. You can compute, given a data, you can compute R characteristic, you have your calibration parameter, you can infer the critical parameter, okay? So let's see how does it work. Remember, this is a very simplified scenario. I have this calibration parameter versus this index of this power law. So if I have different astrophysics for my model, my calibration parameter changes. And then I can go and infer, or at least capture this, this bound of this calibration parameter and trying to infer something to the astrophysics as well as the fundamental physics. And this is more or less how it looks in GR. Now, we can, of course, play this game, and that's what we did in this paper, in a theory-specific way. So in this case, I'm considering a scalar gas bonnet. I don't want to bother you with the details of this theory. It's a quadratic theory. It has a coupling parameter. And then you can see, I'm not telling you what are the parameters of this image, but it looks similar to what the GR case is. Now, we can play a similar game. This is going to be for a scalar gas bonnet in a theory-specific way. We can also do that for the Retsola-Shirenko solution, which is theory agnostic. Remember, when this parameter in this case is called A1 is 0, you recover GR. And when the coupling parameter for this theory is 0, you recover general relativity. And now what I'm going to do is I'm going to fix my astrophysics and I'm going to vary the coupling parameter, or in the theory agnostic way, I'm going to vary this bumpy parameter. And what you see and what we found is that these type of observables are more susceptible to the astrophysics than to the change of the geometry. So this is consistent with the notion that one might need to test modified theories of gravity against like GR in some sense, even if you don't know the calibration. But then the observable at the end of what you can actually going to observe depends drastically or more on the astrophysics than on the underlying theory of gravity. And if you do this game again for a theory agnostic way, as you can see, this calibration parameter changes, but not that much when you change the astrophysics here, okay? So what this means is that at least for this simplified model, and there have been other works on this direction, the astrophysical parameter uncertainties is the thing that dominates the estimation of the black hole shadow size of the boundary, meaning that if you have a departure from general relativity, it's very difficult to distinguish from inaccurate emission of the modeling, okay? So here, and that now it also, we can put in context my previous slide where you see the error bound of the EHT is really large. And the reason why is because it's actually, you are dominated by the astrophysics with this type of EHT observables. Okay, is there a question so far?
Yes, Alejandro, I have one question actually.
Yes.
Yeah. Can you remind me what is this gamma? You have 4 different gammas here, but actually same values, 2 of them. What are these gammas?
Oh, sorry, like you mean here, yes.
Yeah, these gamma values. What is this parameter there?
It is a sort of like, it's a simplification of this model in the sense you have different, you consider different for your equation of state of this plasma. You can assume also different things. So it's a sort of an specific properties of the plasma. So my model, I didn't want to go into the details, but in some sense, you have this alpha parameter. But then here you can see that as soon as I change this characteristic radius and this gamma, which are properties, this is the adiabatic index of the.
So it's a polytrope.
Yes, it's the adiabatic index of the.
Okay. So you're assuming a polytropic sphere here. So how much they will change if I assume something different, like a different model, like a Tolman 7, for example, a sphere or a constant density sphere? You know,
yeah,
like
it won't change that much, and that's actually the whole point. Even if for this simplified model, Camilo, here the most dominant thing that it changes is this alpha, and these other things of the. To close your system, you need this equation of state, and then here R is just a parameter, which is just where this critical point outside. I don't. We can talk about the details, but the idea is that it doesn't change that much.
Okay, got it. Okay.
For this simple model, the one that modifies this. But yes,
okay, cool. Okay,
to be strictly accurate, my astrophysical model depends on 3 parameters. I should have said that. This one barely changes. So you can change this as Camilo was suggesting. It wouldn't change that much. The one that's actually dominated the observable is this alpha.
The alpha parameter. Okay, that's good. Okay, thank you very much.
Thank you. So yeah, so the point here is that, again, and that's my one of them sort of takeaway home I want to draw you from this talk, is that for the current observation, EHT-like observables, the astrophysical parameter uncertainty dominates our estimates of the black holes, of what we can infer from there. So now we can move to ask the question, okay, how will this be in the future? How would higher resolution images be? And then you can say, okay, will it look something like this? And of course, this is not what the EHT resolution can achieve. And then in principle, is saying, okay, this will depend, of course, on the plasma that's making these observables actually possible. So we actually want to have some plasma, otherwise the black hole, we wouldn't be able to observe it through electromagnetic observations. And again, I want to emphasize, all these images will depend on the space-time and the astrophysics, and I want to disentangle them. So let us continue and think about, is there a way or proposals to disentangle these two bits? Now, going a little bit on a theoretical tangent or endeavor, in the Kerr solution, there is a region in the space-time that is called the photon shell, where all the bound null geodesics are allowed. And then what I mean is that they will not escape through infinity. They will not go into the event horizon, and you can have bound null geodesics, photons orbiting in this photon shell. But then the important thing, and that is very nice, is that these bound orbits are unstable. And then this is just allowed, depending on the spin of the black hole, this will live in a particular region. And this is an interesting property of the Kerr solution, this photon shell. What it means is that I can make this nice distinction. So let me pause the simulation. Let me assume there is a black hole here. Then we will have the observer plane of what you're seeing here on the right, sorry. We are observing the black hole at 0 inclination, meaning from top down. And I'm going to start counting photons with this label N. So imagine I have an accretion equatorial disk. So in your image, in the image is like the black hole, observer here. And then anytime my photon crosses the equatorial plane where the plasma is, I'm going to count this as an N equals 0. If it crosses another time, an extra half turn, as I'll show in the animation, I count it as N equal 1, N equal 2. Okay, so this, oh, sorry. So what we're seeing here is the N equals 0. So this is 2 examples of the N equals 0. Now this animation is going to play lots of these N equals 0 like photons. That's going to make this broad structure of the image, okay? But because of the properties of this photon shell, there are photons that can do an extra turn, that are bounding, but that are orbiting in a bound way, but they are unstable. And then they can just make an extra half turn and then go to the observer. So this is 2 examples of two of these photons that can do an extra half turn. Now let's put a lot of them. And this is a property of the space-time. Now you see that the photons that make this extra half turn, they don't appear anywhere in the image as opposed to the previous one. They appear in this structure that we nowadays call photon rings. And as I said, this has been described over the past decades. Now, of course, you can go to N equal 2. So this will be the photons that do 2 extra half turns. 2 examples of those. And then launch a lot of them. And your image will be the composition of all these photons that make these extra turns. And then again, they don't appear anywhere in the observer screen. They appear in a very particular location. And of course, N equal 3 exists, N equal 4, and then what we call as the black hole boundary of the shadow or the critical curve is this N equal infinity. And I want to emphasize that because this N equal infinity means that the black hole shadow is not observable. It's a theoretical curve that we cannot observe because for the photons that are bounded there infinitely many times. We, of course, are going to just observe the photons that escape to us, meaning that the images that we observe are the composition of all these photons doing these extra trajectories, etc. And then the result is this nice image that we can achieve, of course, if we have perfect or a very high resolution image. In reality, of course, there will be opacity, photons will be reabsorbed and absorbed. So in principle, you might not be able to actually see in the image n equal very large. Okay, so that's a little bit of what I need for the theory. Now, we know I'm talking about the Kerr solution. The Kerr solution has very nice properties. In particular, it's integrable. What it means is that I have the same number of degrees of freedom as constants of the motion, meaning that I can totally reconstruct the form momentum of the photon. And that's important because in recent language, and it has been working over the past years, you can write the photon trajectory in closed analytical form. And this is going to be very important for the computational analysis that I'll show in the next slides. And what is important is that you can write this as elliptic integrals. And now the previous structure, n equals 0, n equal 1, depending on what the photons are doing around the black hole. And remember, all that structure is governed completely by the photon shell. It's a property of the Kerr solution. And it's going to be labeled, we can do that, as the number of angular turning points encountered along the trajectory. And again, let me repeat this idea because it's very important for my talk. If I have a black hole and I'm observing it here at the pole, and I have emission in the equatorial plane, I'll have something that I'll call in this talk the direct image. Those are lens rays. But also from the same point, there will be a trajectory that goes from here. It started at the equatorial plane, goes back, crosses again, that's the extra half turn, and then goes to the observer. But from the same point, emission point, there is also this n equal 2 that goes and makes these 2 extra turns. And remember, this whole nested structure of rings, photon rings, are fully determined or characterized by properties of the Kerr solution. Also, what's important here is notice that these n equal 1 photons are actually seeing the back part of the accretion disk if I'm considering an equatorial plane. And this is going to be very interesting. Now, let's go back a little bit to the topic of the talk. Can we use this structure now to disentangle astrophysics from the gravitational part? What is interesting is that the state-of-the-art GRMHD simulations, general relativity magneto-hydrodynamic simulation, the best simulations we have so far for the accreting plasma in general relativity, when you average them over a certain time, that's still not quite certain, I'm going to talk this in a little bit, you find, and this is what was found in this nice paper a few years ago, there is this persistent structure of these photon rings. So here, when you average these GRMHD simulation images, you see this here, the direct emission, then you see this other ring, then you see another one, and in these GRMHD simulations, you can go up to n equals 6, 7, depending on the resolution of your image. But these persistent structures have a very distinct signatures when we observe them with very long baseline interferometers. So if we make a cut on this image, a horizontal cut or a perpendicular cut, and in this is with respect to the black hole spin, we compute the Fourier transformation of this image, we compute then its amplitude, and then we plot it based on your baseline, giving a particular frequency observation. You have your instrument, let's say at 230 gigahertz as the EHT observes, and you have your baseline, that's the distance from your telescope. Then what you can find is that where the EHT is currently observing is this type of baseline. This is, for the EHT, is actually the size of the Earth. You are mostly dominated by the disk jet structure. But if we are able to go to longer baselines, let's say we keep the frequency of the receivers, but now you are able to put a telescope, a radio telescope, farther away, let's say at the location of the moon, you are going to start seeing this structure. So, second important key point for my talk. And it has been realized recently that if you are able to go to longer baselines, then it seems that this part is dominated by the photon ring. In some sense, it's like the astrophysics got forgotten a little bit. It's less astro-dependent. And then you might be able to get these powerful constraints that depend to the black hole and not to the surrounding plasma. So these recent results suggest that conceptually, there is a very powerful new test of the strong field GR, and is measure the shape of the photon ring. And as you have seen over my talk, I have mentioned n equal 1, sorry, n equal 0, n equal 1, n equal 2. You will see why we stop at n equal 2. And in principle, we can consider larger, but more or less you want to know, where am I in this quasi-universal regime, where the black hole sort of forgot about the astrophysical details, and now I am just seeing this nice set of nested rings, okay? So what do we need? And then just to recap, and I'm saying this, we as a theoretical astrophysicist, I'm not part of the Event Horizon Telescope. I'm just a theorist simulating in my computer. In principle, if I want to study and understand these photon rings, as I showed you in a few slides ago, I need a plasma. I need some prescription from the astrophysics. I need a theory of gravity to make this ray tracing. So I produce the plasma behaves in a particular way. I ray trace those rays to the observer. I can compute an image, and then I can compute the Fourier transform and get what is called the visibilities, which is basically the Fourier transform of this image. Of course, the AHT collaboration, they do a super job, which is a monumental task because they are going in the other direction. They are going to measure a visibility. They have to now disentangle these two things and then reconstruct theory of gravity and the astrophysics. This is, of course, a monumental task. The reason is that the measured visibility is going to be the source visibility multiplied by the calibration of these instruments, plus, of course, noise. So you can imagine what they have to do is a monumental task. You have to reconstruct with sparse sampling of this Fourier transform, reconstruct an image. That's why this business is really, really hard to make this observation. And that's why I believe this is a great achievement as a community and for humanity. But for me, my task is way simpler because I'm starting from the left, and then I can compute the source visibility, and I don't even have to go through this noise and residual gains to understand this type of problems. Now, I can also ask the following question: what do we know the most? And in principle, and if you ask me, even though I work on tests of general relativity, I believe for this type of observations, what we know the most is the theory of gravity. It's just GR, and according to GR, you just need, for astrophysical relevant black holes, the spin and the mass of the system, and that's it. But the parameters of the plasma and in these simulations are less known. What's the configuration of the magnetic field? Well, as Camilo was asking, what are the properties of this plasma? How that impact my observable? And in particular, you can also ask, what is the computational cost to study this? So GRMHD simulation, general relativity magnetohydrodynamic simulations are insanely expensive. So for example, I know that the AHT had a simulation library of like 20-something terabytes of space where they just had 43 GRMHD simulations. This is how expensive it is. This is hours and hours of supercomputers, and they had basically a few spins. They study -94, -5, 0, +0.5, +94. They have two main models, one that they call MAD, and that depends on the configuration of the magnetic field, or SAME, but in reality, this is very, very hard to study, and that's why it's so hard to do this type of simulation. Then ray tracing is fairly simple. You, in principle, can just integrate the geodesic. Fourier transform is also very cheap. Actually, the codes that we use and the algorithm used nowadays is called fast Fourier transform because we can do that fast. So what we have developed, and actually the paper came out last week, it's a framework that we call AART, Adaptive Analytical Ray Tracing, which is taking part of this, and it's able to reproduce, as I'll show in the next slides, this type of observables to study photon rings and the variability of those photon rings to, as I mentioned a few slides, see if we can disentangle the astrophysics from the theory of gravity. This code is open source. It's available on GitHub. The paper description of the code, as I said, came out last week. And I'm going to talk for the rest of my talk, why do we mean by adaptive analytical ray tracing and how we're doing this in a fairly inexpensive, computationally speaking, way. Okay, that's the rest of the talk. Questions so far?